Yeah, maybe I had like a sub title, which is just story time with Dan. Yeah. So I'm essentially going to tell you the story of how categorical symmetries work. Yeah. So this section of the lecture is going to be mostly illustrative, and it's not going to be nearly as technical as any of the other things I've given you. Categorical symmetries really are just like another entire type of technology that you need, or there's an entire new set of tools you need to even like really properly describe it. So I thought it would just be nice to talk to or tell you guys sort of give you a flavor of what categorical symmetries are. So I wanted to start with sort of it's not a baby version, but it's sort of historically what people did first, which is called higher groups. And actually, this was sort of my introduction to the field, was with how higher groups work. And then I sort of filled in for myself all these details about how you actually go in and do stuff that's useful with the higher form symmetries. So, good. So we've talked a lot about higher form symmetries, and now you can, I mean, if you haven't already seen it, there's like a bunch of bad naming conventions in the field. Everything's higher, everything's generalized, everything's a form. And so this one is slightly different, and I wanted to describe to you how it works. So again, a higher group has some degree. Everything's, essentially we only have like 3 words for everything. So anyways, there's some degree n, which is a non-negative integer. And then instead of a single group, we have a collection of groups that go from 0, well, I'll write it suggestively, it goes from 0 to n minus 1. Okay, so together we write a, such an object is called an n group, and it's usually written in a very compact notation as a boldface G for the number n. So usually people then just say, you know, the Gn is the set of all of these groups. And then there's some extra data. And so I'm going to try to describe to you what this extra data is. Okay, well, maybe before I tell you what the extra data is, I should tell you, what this data is. So the idea of a higher group, or an n group, is that you have a collection of higher form symmetries. And in general, they're nested. So what I just said really doesn't make sense. A 0 form symmetry acts on 0-dimensional operators, a 1 form symmetry acts on one-dimensional operators, etc. So what does it mean for them to mix? So let me first draw a picture for you. So let's see if I can draw a nice picture. So if you take 3 of these symmetry defect operators, like this, or so if you take 3, you can sort of intersect them at a junction like this. You can alternatively think about this as you take 2 symmetry defect operators, UG1 and UG2, and you sort of collide them, and then you get your UG3. At any rate, the point is that this is so if this is a 0 form symmetry, this is a d-1 dimensional symmetry defect operator, but the intersection is d-2 dimensional. And so if you had a 0 form symmetry, you'd say, aha, now I have something that looks d-2 dimensional, which is exactly what you would need for a 1 form symmetry. So essentially the point of a higher group symmetry is that the 0 form symmetry, you can have all sorts of weird intersections that get as low of a dimension operator as you want. And so what that means is that actually the 0 form symmetry mixes into all of a higher group structure. And essentially that story just continues for every different component of the higher group. So then the 1 mixes up as well, etc. Except that the highest form never mixes with anything because it's already too low a dimension. So there's many pictures like this you can draw where you'd say, well now if you do something weird, you can get some sort of like a one-form symmetry defect operator here, H. But I don't want to draw all these pictures because this is about as good as I can get. Sure.
So in that picture where you say that G1 and G2 are colliding, why is that not like just taking the group products that you wrote down earlier? What is different?
Yeah, exactly. So yeah, so this the zero form symmetry. This is what essentially a higher group is that the zero form parts do form a group, except that their intersections can act on like line operators, for example.
So I would say that this can I say that UG3 is U of G1, G2?
Yes. Yeah.
And so, but I just don't, in that equation, that composition equation, I just don't see those lower dimensional symmetry defect.
Yes, exactly. This is essentially how the categorical structure works. Is that what you can always do is just restrict to sort of a single level. So this is, I'm drawing it actually suggestively. So it's like, I can just think about the action of the zero form. There's a group law. That's great. But when you sort of then you take into account the junctions and you're like, oh no, there's some G1 action as well. And then if you just keep looking at low and lower dimensional intersections, then you find that actually there's this whole structure. And that's what a higher group is.
Okay, and are you saying that for any theory with let's say zero form symmetry, you would actually have this entire structure, but perhaps sometimes the rest is trivial or so? And
yes, exactly. So that's actually why I drew this picture at the very beginning. Maybe I'll draw it later.
And is it guaranteed that, let's say, that it's always everything?
Sorry, I'm just going to draw the picture I drew at the very beginning. So we started with the higher form symmetries. And these are really just a subset of higher groups. So as you said, or as we said, that we know how higher form symmetry works. And as I was saying, you could just sort of, if I just close my eyes and only look at the zero form parts, this would look exactly like a group law. But then once you take into account, or once you start looking at all the junctions, you can see that there's all of this higher structure. But you can always just say, well, that structure is trivial. And you say, well, there's no operator here, it's just the identity operator. And then you just restrict yourself back to the higher form.
Okay.
So that's...
And maybe I should just be patient, but I'm just wondering, suppose I know that I have a zero form symmetry and one form symmetry in a given theory. Is it guaranteed that when I fuse these zero form guys that I will meet the one form symmetry there? Could I have a one form symmetry without a zero form symmetry? Let's say.
Yeah. So good. So as you said, there's many ways that you can trivialize it. So if you just wanted a zero form symmetry, you could say all of these arrows are trivial and all the groups are trivial. But you could have also said, I just want it as one form symmetry. And so this is trivial, and therefore all its arrows are trivial. So you can start from here to here.
Yeah. It could also happen that the zero form symmetry never sees a one form symmetry, even though there is a one form symmetry.
Yeah. So there are cases
sort of disjoint that.
Yeah. So for example, if you could have a case where this is actually some G10 times G20, and only one of these has arrows, for example.
Okay. In this figure, this UG1 and UG2 are ending at the intersection, right? But I could also have sheets that extend beyond each other, intersect, but cross through each other.
Yeah, so usually, good. So I was trying to emphasize that this, you can really think of it as saying like, okay, now let's just do a top-down picture so I can draw it nicely.
Yeah.
So imagine you have a G1 and a G2. So you can imagine is sort of, pinching them at the ends. and then just like squeezing it like a Ziploc all the way up. And then that's sort of the picture I was trying to draw. Is that like you've taken the fusion on this bottom half down here, but not up there. So that's more common.
Okay. But I can cross them.
Yeah.
Then.
So usually, right. So this is where the category theory starts to get important. So right. So I only really tried to stay away from everything that wasn't a simple fusion. Right. So if you had 3 of them, you can do this sort of fusion.
Yeah.
But then you can imagine trying to change the ordering. And when you change the ordering, there's some point where you imagine sort of taking this leg and moving it up. And at some point you cross, and there's a 4-according junction.
No, I meant that crossing could extend beyond it. Can it not?
So yeah, so you're going for something that's even more complicated than what I just talked about. You're talking about taking this picture.
Yes.
Yeah. So before you do 6 legs, you have to do 4 legs. And then you can do 5 legs, and then you can just keep working out. But it turns out, since these are all topological, there's some rules essentially that are dictated by the theory usually about how all these junctions work.
Yeah.
And this was the category theory I was trying to avoid.
And you will define what a 2 group is, for example.
Yes. So I guess one of the main messages of my lectures are that this is a very nice way to think about it, and it's very nice and pictorial and makes for a really good colloquium. But in terms of actually analyzing a theory, it's not super useful, I think. Although people might be mad that I said that. I think it's actually much more important, or I always like to try to emphasize the background gauge field perspective. So let's try turning on some background gauge fields, and I'll tell you how this mixing happens. Because it's much more concrete than saying I have some intersection and then something happens. And so for G0, let's say we turn on the background gauge field to 1. For G1, we'll do A2, and so for more generally for GP, let's have A P plus 1. Okay? And so the standard, and we'll say that their standard variation, background gauge transformation is D lambda P. Okay. So this is what it would look like if you just had a product of higher form symmetries. A higher group symmetry is more complicated. So let's fix P and look at its gauge variation, or its background gauge transformation. So this is a higher form. And so this is what happens in the empirical higher group. So a higher group is you still have the same transformation. This is a sort of first order transformation. But then you have
this P is the degree of the form or the group?
It's the degree of the group. Or like, the level we're at. So then you have a contribution from every lower level. We do something like lambda Q. It's P minus Q. Yeah. So that's maybe not super helpful. But what I'm saying is that if you look at, for example, so for example, you take the transformation of the lowest couple. So the gauge transformation of the 0 form part is just d lambda 0. There's nothing below it, so nothing can mix into it. But then the transformation of A2 of the 1 form part is going to be its own transformation. And then the only thing below it is the 0 form. So you can have something that looks like some constant k times lambda 0 So if we just stopped here, this would be what we call a 2. So now we can do another one. So see if we can do the 2-form symmetry. So you have d lambda 2 plus, so you have one term, which is lambda 0 k1 with da1 plus k1 lambda 1. I think actually this term is not allowed. I think this term is not allowed because it sort of would be dependent on the gauge transformation twice. So, anyways, sorry. So then you have dA1, and then you can also, oh, okay. I'm just going to write them all because I'm not actually sure. I'm sorry. 0, dA2. I think these are probably the only 2 terms. Okay, so now if you stop here, this term is this is a 3 group. You know, we can continue going on, but this is essentially the whole point, is that, yeah, this is the point.
This is just the definition.
This is the definition, yeah. Yeah. So, right, so this is some formal structure, great. Why does this even exist?
What is the counterpart? I mean, it's not probably relevant for your lectures, but like a group, I mean, you can define a gauge group like this, but a group is like closed and associative or whatever. What is a 2 group like that, algebraically?
Sorry, so are you looking for a space? Like a geometric space? Or
No, just algebraic 2 group.
It's a category.
Okay.
Sorry. Unfortunately, everything's a category. And
So 2 group is a category of what sort? I mean, categories are variables and morphisms.
yeah, right. So I think you could say I think there's actually 2.
Of the scenarios.
There's two types of. There's 2 ways you can represent it, and they're dual. One is that it's an invertible 2 category, I believe, and the other one is that it's a modular. It's a type of modular category. Yeah. So a modular category means that there's a in addition to. Okay. Sorry, I'm not going to define it because I didn't tell you what a category was. So I don't want to get too far or outside of the reach. Good. So now I'm going to give you an example of where you get a higher group in a normal quantum field theory. And so the simplest example is that of a 2 group. So let's take a 4D. Let's just take 4D QED with 2 direct fermions, which is the same thing as 2 Weyl fermions with positive charge and 2 with negative charge. Okay, so I'm going to just write this as, write the action as m squared plus psi bar plus, and then the psi minuses. So this is your action, it's just normal QED. But now we want to specify a 0 form symmetry. And I'm just going to call it U1 sub f for flavor. So we have psi plus 1, psi plus 2, psi minus 1, psi minus 2. So these have charges plus 1 and minus 1. And since you have 4 of them, this is a vector symmetry and there's no gauge anomaly. And now if you're either smart or perverse or I don't know what else I'm going to call it, you can pick this symmetry, which is kind of silly. take P not equal to Q. So this is just some symmetry you can pick. And if you, and it has, oh, this theory has some anomalies. I picked this specific structure. So first we said there's no gauge anomaly, so I'm going to write that as G cubed is 0.
So here F stands for what?
Yeah, I should probably not use that for everything. I wanted to use it as flavor, but yeah, sorry. I realized there's sort of only 3 letters in higher form symmetries. There's B, there's A, and there's F. And yeah, I've definitely caught the sickness, unfortunately.
So here 2 flavors and here fermions.
Yeah. Yeah, so these are the Dirac fermions, and this is their vital components. That's why I wrote it that way. Sorry. Right. Okay. So we can look at all of the anomalies. So there's 4 possible anomalies. There's the one. So we can just compute the triangle diagrams by just taking trace of the generator cubed. So this is the gauge anomaly is 0. Again, this is also a vector symmetry because these cancel against each other, these cancel against each other. So trace of this F cubed is 0. And now we can look at the ABJ anomaly, which is G squared F. And since these all square to the same, and these sum to 0, this one is 0. But now, if you look at the anomaly with 1 gauge leg and 2 flavors, you find that it's not 0. You find it's 2p squared minus 2q squared. And I'm just going to call this coefficient kappa. Okay, so the anomalous variation of the action is going to look like kappa times lambda 0. Oh, crap. Okay, sorry, I ran into the same problem again. F sub F, F sub G. So sub G is now the gauge field strength. And so this is going to be the anomalous variation of your action, which comes from the variation of the measure in the Parkinson function. And so, this looks kind of weird. But what's nice is that something that we didn't talk about yet is that, or I didn't bring up yet, is that this theory also has a U1 one-form magnetic symmetry. There's no electric symmetry because there's sort of a minimally charged fermion, so that there's no projected Wilson line. But there's no magnetic charge, so you can still have magnetic line operators, and that's fine. And so if you recall from one of the earlier lectures, the conserved current for the magnetic symmetry is the field strength, the dynamical field strength. So you can really write this as kappa times lambda 0 F, so F wedge J. And now we know that if you turn on a background gauge field for this symmetry, you add a term to the action, which is, right here, which is I B to wedge, there's a star in here, star J2. Cool. So now what you can do is you can upgrade the normal variation of this B2. So normally B2 is some D lambda 1. Now you can upgrade it so it exactly cancels this anomalous variation of the action. So you would say this is minus kappa lambda 0 F sub F. And so now you see that actually this anomaly is not there. If what it's telling you actually is that the zero form flavor symmetry of this type lives inside of a 2 group with the magnetic one form symmetry. So this is one way to write this. And something interesting I want to point out is that, so this is a weird symmetry. And you might ask, what is it good for? It turns out the lowest dimensional operator you can write down in your theory that preserves this symmetry, and I think no other symmetry, is a 4 fermion term. So this is interesting because of a problem called symmetric mass generation. And I don't want to really talk about that now, but you can ask me about it later. It's very interesting.
So before, let's say, this understanding of one-form symmetries, we would have said that this theory doesn't make sense, right? Because it has an anomaly.
Yeah.
And now you're saying that with this additional terminally action, additional background gauge field,
Yeah.
you can actually make sense of it.
That's right. So yeah, good. So you would say, for example, that this anomaly prevents you from gauging this this U1 symmetry. But what it says is actually you can gauge it if you in addition gauge the magnetic one-form symmetry with this weird gauge transformation parameter.
Okay. So,
Yeah. This is also known as the Green-Schwarz mechanism from string theory.
so are we adding is B2 now dynamic or background?
Yeah. So right now everything is just a background gauge field, but you can gauge everything.
I'm just trying to understand what you mean by gauging the one-form symmetry.
Yeah, so good. So you could make this a dynamical U1 two-form gauge field.
But is that necessary to make sense of the theory, or is it good enough to just add this background?
You would need it in order to make sense of the gauged theory.
Sorry.
Yeah, what's up?
I might be getting things wrong, so let me first answer my question. If I understand correctly, you have some fermions that have some magnetic and electric charge, right? Here some fermions.
They only have electric charge.
Only electric charge, okay. So typically, we will say that if I have some electron with some charge B, then I'm breaking the U1 electric force symmetry
Yes.
to a subgroup, to a set B, essentially. But it's also like a two-group symmetry. So I wanted to know what is the relation between these two ways of thinking about this kind of thing, right?
Sorry, which part would be a two-group symmetry? If you break the electric one?
Yeah.
No, I think for just pure QED that this is the only two-group. I don't think there is a two-group involving the electric symmetry.
Okay.
There is an interesting story about gauging the subgroup of the electric symmetry, how that has to do with the two-group. But I can tell you about that later. Okay, so I told you how, and now maybe I'll tell you why. And by why I mean, or what is it good for? Why do we care?
But so one more
Yes.
question. So the U1F is obviously not you're just doing on a background for that, but that's never becoming dynamic.
It's never what?
The U1F is never getting dynamics. Right? That stays
Yes.
in
Yes. But you can give it dynamics. I thought that was what your question was. If you want to.
No, my question was my question was about the B2.
Oh, okay, yeah.
So, because B2 is the question I was just asking, or the previous question?
Previous question.
The previous question was about B2. If we add if we add kinetic terms for B2.
Oh, yes, you can, yes, good. So you can add kinetic terms for B2, and without adding kinetic terms for F. F sub F.
FF.
Yeah.
Okay. But that's not, my question was if that's necessary for this theory to make sense.
Okay, good. So this is actually something that I'm going to, it's related to what I was about to say.
Okay.
So, so I drew all these arrows in a sort of nice, well, they're either nice or complicated way, depending on how you want to think about it. But another way to say that there's this arrow structure is to say that there's some sort of nested structure of the in-groups. So So if you have the total n group, if there's a sub n group where you start at only the G1s and go up. So the total n group is you include everything from G0 to Gn minus 1. Then what you can do is you say, well, I turn this one off in all of its background gauge transformations, and I look at here. So now all the transformations populate everything here. So you can say that there's an n group starting at G1. And similarly, you can just keep truncating your n group as far, maybe no parentheses in here, to n, all the way to saying that you start at the n minus 1, which is just the same thing as saying you have an n minus 1 symmetry. So what you can do is you can always gauge a subgroup of the full n group symmetry. You can really think of this exactly like having a group that has subgroups, proper subgroups. You can always gauge a proper subgroup of a full group symmetry. Similarly, you can always gauge a proper sub n group of a full n group symmetry, which I think is kind of what you were asking, Sam. Is you can make the one form symmetry dynamical without making the zero form symmetry dynamical. But if you try to make the zero form symmetry dynamical, you need to make the one form symmetry dynamical, because it's really a two group and not just a zero form symmetry.
Yeah. Okay. I think that was that was related to my last question. Yes. But my first question was actually if it's necessary at all for this theory to make sense.
Oh, no. You don't need to do n groups at all for this to make sense. You can just analyze this.
Yeah, so you can keep B2 as a background gauge field and specify this transformation if that's good enough.
Yeah.
Then it makes sense.
Yeah.
Okay.
But there is some power in realizing that there's an n group structure. And it comes from the fact that you have this nested structure. So, again, I like to think about RG flows a lot. So if I give you some theory with an n group symmetry, you can ask about every possible UV theory that flows to it. And if this theory has no n group structure, what it means is that the n group structure must emerge at some point, some intermediate energy scale going from the UV to the IR. But what's interesting is this fact that you have this nested structure. What that means is that you can actually have this part emerge, and then the next one emerge, and then the next one, and the next one, and the next one at consecutively lower energies. So if you have some energy scale here, E sub P, where the P part of this P sub n group emerges, and you have E sub Q, where the Q's part emerges, P has to be bigger than Q.
So why do we assume that the UV does not have any?
If you assume. This is actually interesting, is that if you have a continuous two group, it is not, or sorry, a continuous n group is not consistent with conformal symmetry. It's a trivial structure. Actually, I only know that proof for two groups, but I believe it's true in general. But anyways, so this is sort of the reason why we think of these as usually being accidental symmetry. And in general, they really only occur in sort of effective field theories. So like QED, for example, there's no mass, but there is a scale set by the theory. So, right. But so the point is that these energies have some sort of hierarchy as they emerge. And that's incredibly powerful because these energy scales can be totally tracked by the fact that they correspond to the emergence of what looks like a classical P form symmetry. So essentially EP is the energy where the P the p-dimensional charge operators become stable. Or they merge, whichever way you want to think about it. And so I want to give you one example of why this is useful, because this theory is great to show that it exists, just show that there is a structure or how it emerges, but it's not the most interesting theory. A theory that is interesting is 4D theory of SUN axions. So axion QCD, or well, you could do either axion QCD or just axion angles. This theory has a 3D symmetry. So here there's a U1 two-form symmetry, and the charged operators under this are the axion strings. And there's also there's a Z and one-form symmetry where the charged operator are the Wilson lines. So one way you might see that there's something very funny going on between these two is that when you turn on, so the axion coupling is this. So essentially it's the same theta angle that we're writing down, except you turn the theta angle into some dynamical field, which we call A, and that's the axion. So F like F. So this is the interaction here. So the axion is a periodic scalar field. And usually people write it as, there's this parameter Fa, which is called the axion decay constant, which determines the periodicity. But essentially it's just a periodic scalar field. So you can think of this like some dynamical theta. So this is like a theta term. And as we discussed, when you turn on a background symmetry here, or background one-form symmetry, the periodicity, or the quantization of the instanton number changes. And so that seems like it would be bad because the axion is a periodic scalar field, and you can't sort of just break the periodicity. But it turns out that there's actually a higher group structure that emerges when you try to do this. And what it is it's mixing these into here. And so the question you might ask then is, what does this hierarchy imply? So in this theory, you only have to worry about two scales. So you have this sort of two-form energy, and this is going to be set by the tension of the axion string. So now I need to tell you something about axions. Is that in most four-dimensional models, unless you want to try to take some UV completion, that's a five-dimensional theory, the axion you can realize is the phase of some UV fermion. That's just some magic I'm going to draw for you. But so what it means is that the energy, this energy scale where the one-form symmetry emerges, is given by whatever the mass of that charged particle is. And so the fact that there's a three-group symmetry here tells you that any UV completion of axion theory has to have the axion string tension is higher than whatever the mass of these heavy fermions are. So yeah, so that's kind of cool. And what's neat is that this is a totally UV completion independent theory, or independent constraint. And in fact, if you look at any UV completion, you can check how loop corrections affect this, and you'll find that there's some weird runaway direction where your theory becomes strongly coupled, unless this is evaded. Yeah. Okay, so now we're running a tiny bit short on time, so I want to tell you maybe something cool about, or tell you more generally how categorical symmetries work. So one of the things we tried to emphasize, during these lectures, is that given any symmetry group, you can associate some sort of symmetry defect operator that enacts the symmetry action on some charge operators. So in general, we give a higher form symmetry. You have these obeying some group law. But that's not the most general sort of multiplication you can have for topological operators. It turns out there's a lot of sort of weird things you can write down. And yeah, so instead of writing U sub G, which we were sort of using for group symmetries, I'm just going to write some topological operators D. So if you take the product of any two topological operators, you don't necessarily get a single topological operator. More generally, you get some sum, direct sum of topological operators. So you take the product of two, you can sort of pull them apart like an accordion and get all sorts of different things.
What are the CIJK?
A CIJK are some numbers.
Can be complex numbers, or
yeah, these are kind of like, well, they're sometimes called quantum dimensions, but this, for example, shows up in two-dimensional CFTs, where you have topological lines, and then these are the, this is like the Berlin array.
Then they are integers, right?
Yes, that's right. Well, in those examples that we have in mind, yes. But I think, and more generally, they don't need to be integers.
Okay.
So this is one way that you can sort of break your sort of notions of what a symmetry means. This is definitely not a group. And this is one of the ways in which you need to have category theory. There's an even more dramatic version of these.
IJ are valued where?
In some set. It's in some category. Sorry. But so there's actually an even more dramatic way that you could have some symmetry that doesn't look like a normal group symmetry. So if you have some di and dj, what you can do is you can multiply them together and get some single operator k with some topological quantum field theory living on it. This is also something that shows up and is actually very strange. But if everything's a topological operator, there's still some notion in which it can act on operators as a symmetry. And so these are some of the weirder notions of a symmetry category, or a categorical symmetry rather.
Yeah, maybe just actually to come quickly back to Pratik's action question, not action. So these I and J, I shouldn't think of them quite as analogs of these G. They're not group elements.
In general, no. Yeah.
They're objects in categories, groups or higher groups or.
Yeah. In general, it's just some set of objects. Yeah. But so I thought that maybe rather than just trying to describe to you how some of these formal things work, I would just give you an example, and that can be a way that we end everything. So sorry. Now the very last circle. So right, I promised this example to you yesterday actually, which is we're going to look at SUN QCD in 4D. So let's take SUN gauge theory with a single direct fermion in a fundamental representation. Okay. So this theory has an action. Squared. So this theory has a classical U1 global symmetry, which rotates psi by a chiral phase. Sorry, I'm going to change what I just said. I'm going to take this to be in the adjoint representation. So everything is still the same, except change the representation. So this theory has a chiral symmetry, and it rotates the field this way, but there's an ABJ anomaly. And so let's make this generator F, because I don't know any letters. And the size of this anomaly is 2 times n. And so what that means is that this U1F is actually broken into a Z2n chiral symmetry. So this theory also has a one-form symmetry. There's a Z and one-form center symmetry. And as we've said now many times, when you turn on a background gauge field for the center symmetry, the instanton number is quantized. So trace of f wedge f over 8 pi squared is n times n minus 1 over 2 b with b over 2 pi squared. And this is valued in 1 over 2n times z.
Sorry, I think I missed this. What are small f and small g?
F, so G is the, yeah, so this is I'm saying this is the coefficient of the ABJ anomaly. G is like the gauge field, and F is this chiral symmetry. Yeah, sorry. I don't have good.
These are things that go in the diagram.
Yeah, that's right. So maybe said differently, the magnitude of the U1F times SU and squared anomaly is 2. Good. Right. So now if we again look at this transformation, so we know that the ABJ anomaly is this because this transformation generates a term in the action which is 2n alpha times the instanton number. And so alpha has to be 2 pi. 2 pi over 2n value, which gives us the C2n. But now if we look at this chiral transformation with the one-form symmetry turned on, we find that delta S is now going to have a different normalization. It's going to be I alpha times 2n times n minus 1 n. B2 goes into I, which is I alpha times 2n times 1 over 2n value. So what that means now is that this Z2n chiral symmetry is actually broken even further by turning on this one-form symmetry. So what that means is that there's actually a Z2n times Zn1 mixed anomaly. So if you have an ABJ anomaly and a center symmetry, you actually are automatically given a mixed anomaly like this.
So can you explain this last part again? So what is the delta S now?
Good. So right. So the chiral transformation here is broken by instantons, and it's broken unless it's literally broken unless alpha is 2 pi times little n over capital N, 2n. this is the restriction of U1 to Z2n. If we turn on the one-form center symmetry, it changes the quantization of the instantons so that it's 1/2n valued. So if we turn on this center symmetry and look at the transformation again, we find that there's this anomalous phase. Essentially, if you turn alpha to 2 pi little n over big 2n, you find that it's going to be 2 pi n over 2n valued. And so what that means is that you have this anomaly, and this is something that has to be tracked from UV to the other. And it can tell you about how adjoint QCD actually has 2n back to it. Sorry, n back to it. That's definitely jumping ahead. But there's
so maybe what was the importance of the adjoint Dirac Freeman?
What was important is that I needed a one-form symmetry. If you have something in the fundamental, then there's no one-form symmetry. Yeah. So I want to tell you in the last maybe 10 minutes about some crazy formal thing that people have invented that allows you to save the symmetry even when you gauge the one-form symmetry. So this anomaly can be written in terms of a six-dimensional polynomial. So the anomaly is now, of course, little f, which is the field strength for this Z2n factoring gauge field. And then it's wedge B2, wedge B2, up to some coefficient. And so if you gauge this B2, now this is some dynamical field strength, or it looks like a dynamical field strength. And this is again an EVJ anomaly that completely breaks the Z2n. So if you gauge Zn1, Z2 and 0 is broken to 0. And something I didn't say, which is maybe important, just for general knowledge, is when you gauge the center symmetry of a theory, you actually go from G, the gauge root, to G mod whatever the center is. So in our case, this is SUN mod ZN, which is sometimes called PSUN. But anyways, so when you go to PSUN theory, your center symmetry, which you gauged, has now turned into a magnetic one-form symmetry. And so if you try to make the zero-form symmetry defect operator for the chiral symmetry, so we leave the 2 pi over 2n, the integral of jf. You find that this is now this is anomalous. So the equation of motion for this J5 is this B wedge B2 wedge B2 times some coefficient here. So that means that this operator is not topological, and you're totally screwed. But there's something you can do to make it topological. So 2 pi n over n. So what you can do is you can take this operator. So I'm going to draw it. My operator is codimension 1. It acts on maybe local operators, psi. And what you can do is something very dramatic, is that you can put a topological quantum field theory on this. And there's some very particular type of topological quantum field theory, and so where you put in a one-form symmetry. In this case, it's a magnetic one-form symmetry. So we'll call it field strength B2M. And it exactly cancels this variation. So this is now where the story time really begins. I'm not really going to write any more equations. So essentially the point is that you have some operator that's no longer topological. It's broken by what looks like an ABJ anomaly. But what you can do is actually put something in here. You can put a topological quantum field theory on your symmetry defect operator that recovers the fact that it's topological. But now, instead of having just a nice product from the symmetry defect operators, you have to worry about taking the tensor product of topological quantum field theories. And that's sort of maybe an esoteric notion, but what I mean is that if you take the fusion of two of these defect operators, you find that there is a topological quantum field theory living on the resulting topological defect. So this is one way that people are trying to use formal things in order to try to save symmetries when you do some sort of gauging like this. Right. So maybe really quickly. So this is sort of the most complicated version of this, which I probably should not have done. But this also happens, for example, in QED. So again, if you have the same chiral symmetry, and here the E1 chiral symmetry, which I'm now going to write E1 and 5, is completely broken by the ABJ anomaly, because you get some delta S, which is I alpha integral F. And again, when you turn on right, okay, good, yes. So here you don't actually need center symmetry. You find that this current is broken by instantons, or rather this is just broken by the ABJ anomaly. And now if you try to construct the symmetry defect operator, because of this equation it's not topological. But what you can do then is to put some topological quantum field theory on the boundary. And so if you take the group element, which is 2 pi over n, then you can actually write down explicitly what this is. It's putting some 3-dimensional vector field, and then you have an action which is I over 2 pi. So it's like a BF theory, or it's really like a Chern-Simons theory. Sorry, the n doesn't go there. The n goes over here. Plus n v1 which F. And it turns out, if you integrate out this gauge field, what you find is that the variation of this exactly cancels the variation of this, so the total object is topological. And then when you can actually try to compute the fusion of two of these operators, and you find essentially that you get too many topological quantum field theories in order for sort of everything to be a group law. And again, since this is the sort of more physically interesting case, we'll go back over here. Sorry, I think this is actually just a bit too. Okay, let's stop. So essentially the point is that here you actually need the magnetic center symmetry, or sorry, the magnetic one-form symmetry in order to make this process work. And so again, you sort of actually find that there is, the existence of this symmetry also sort of tells you that there's an energy hierarchy. In the sense that you need to have first, so if you had some PSUN QCD down here, so, sorry. So imagine you want to have some UV completion of PSUN QCD. You would again find that there's some energy hierarchy. And essentially the point is that you can't have this non-invertible symmetry. Or the non-invertible symmetry has to emerge at a lower energy than the one-form magnetic symmetry. Because this requires the magnetic one-form symmetry. I'm just going to tell you that and you have to believe me. But what that means is that there's no sort of chiral classical symmetry until you have some one-form magnetic symmetry. So this is again some sort of constraint you can find from non-invertible symmetries. And one last comment to make is that so here you have this sort of non-invertible symmetry as well as over here. But these non-invertible symmetries can themselves also have an anomaly. And essentially what happens is you can inherit an anomaly from this classical symmetry. So this cubic, essentially this classical symmetry has two anomalies actually. There's the ABJ anomaly, and that's usually where we stop. We say ABJ anomaly, no symmetry, don't care. But this also has a cubic Tuft anomaly. And so when you save the broken anomaly by the anomaly that's broken by the ABJ, the symmetry that's broken by the ABJ anomaly, once you save it, it actually does have this cubic anomaly. And that anomaly has to be matched along the RG flow. And so that is actually something interesting and important in sort of a new development from these generalized symmetries. And I think that's all I have for you guys. So, thank you.
All right. Any questions? Otherwise, I suggest that we thank Daniel once again for a very stimulating set of lectures, albeit high level, very stimulating. And so, yeah, you can still ask Daniel questions for the next hour and a half, but then after that you're leaving. There will be, today there's a braai lunch. There will also be a vegetarian option, and the meat is all out.
Expect those minutes.
Yeah.